Hello everyone. In this video we are going to talk about limit properties or limit laws depending on who you're talking to. And we're going to start with some basics. Given a certain limit exists, then when we add, subtract, multiply, or divide, then that limit will still exist and we can find it with addition, subtraction, multiplication, and division. In general, these are very straightforward, other than the division part where we have to make sure that the limit of the denominator does not equal 0, because when we try to divide by 0, bad things happen. So all of these are predicated on the fact that the functions are continuous. So what does continuous mean? Well, continuous means that there's no holes in it, and it continues without end, both into the negative infinity as well as to the positive infinity. As long as there's no holes, there's no weird things, then the limit will exist. So as long as we have a continuous function, then the limit will exist and these properties will hold perfectly fine. So the question then becomes, is it continuous or not? As long as it is continuous, then we're fine. Okay, so that is part of what this 2.4 theorem says. As long as you are dealing with polynomials, then the limit will exist. Polynomial being an equation of any length that has whole number exponents. So as long as you have a whole number exponent, that counts as a polynomial, and all polynomials are continuous. As long as we have continuous, then we're good. The weird part is with rationals, because we will have asymptotes. So as long as we stay away from the asymptotes, then we will have limits. Asymptote being the only time when a rational function is not continuous. So let's take a look at some examples here. So for this first example, it says find the limit as x approaches -3 of 7. Well, 7, this is a constant function. It is perfectly horizontal. So the fact that we're looking as x approaches -3 really doesn't mean much, does it? Because the function never deviates from the number 7, and thus the limit will be 7, no matter what x we're looking at. But it's also a continuous function because it is a constant function, and all constant functions are polynomials. So what about example 2 here? We have, this is a linear function. All linear functions are either increasing or decreasing. Both of those, either always increasing or always decreasing, means that they are still continuous, and thus we can find the limit. So the limit as x approaches 6, other than the constant function, which was the same everywhere, this one does change. So we actually have to do a bit of math here. So we will take this lovely x as x approaches 6. We will put it into our function as a substitution. So as x approaches 6 would give us, substitute the 6 in for the x, and calculate, so that's 12 minus 4. So the limit as x approaches 6 of 2x minus 4 equals 8. Now in this next one, this is a rational function. Now all rational functions will look something like this-ish. Depends. But something like that, where you have asymptotes. But as long as you stay away from the asymptote, asymptote being a line that the function approaches but never touches, asymptote, just like that, then as long as we stay away from asymptotes, the rational function is continuous and the limit exists. And we can find it the same way we did with example 2. So since we are focusing here on as x approaches -4, well, we have an asymptote at x equals -4. Well, the asymptotes we really care about are the ones that have 0 in the denominator, right? Those are the ones we really care about. So if that is the case, then my denominator would be 0. So I can very quickly figure this out as 8x minus 9 needs to stay away from 0 for the denominator part. So 8x does not equal, and x does not equal 9/8. So as long as x is not 9/8, then my denominator is not 0 and my limit exists. So I can figure this out. It's the same way we did with example 2, simple substitution. Grab your calculator to help yourself out. So we care about as x approaches -4. Be careful because this is a negative in that lovely square, so we will need to pay close attention to our negatives here. If we type this into our lovely calculator, what do we get? We'll get positive 41 in the numerator and negative 41 in the denominator. So that will give us -1. So the limit as x approaches -4 of this rational function is -1. Okay. So let's take a peek at the next one. Okay, so here we have a rational again, but we also have a radical. Now radicals are a bit weird. If you remember, they only exist in the first quadrant where everything is positive, but we also take care to the denominator not equal to 0 part. So that's what we really care about for here. The asymptote is what will get us. So as long as we confirm that our denominator is not going to be 0, then we should be able to find the limit with simple substitution. So let's see here. We have 3h plus 57 under the radical minus 1 does not equal 0. So 3h plus 57 does not equal 1. Add 1 to both sides and then square both sides. 1 squared is still 1. So 3h does not equal minus 57. So that would be minus 56. So h, as long as h is not negative 18.67, then we are golden. And since the h we care about is 8, we're fine. We can use simple substitution, and we can find our limit. So, grab your calculator. Now, when you're putting this into your calculator, be very, very careful about where your radical ends. If that radical is, if you're not careful, you'll end the radical in the wrong location and your calculator will spit out a weird, something weird. It will be an answer, but it will not be the correct answer. So if you want my recommendation, I would say to deal with the radicand and then work with simplifying the radical. So 3 times 8 and then plus 57 will give us a radical 81. So that is easier to avoid mistakes. So square root of 81 is 9, so 64 divided by 8, and we'll get 8 for our limit. So the moral of the story is, as long as you are dealing with polynomials or any other function that is continuous, then you can find their limits with simple substitution. The problem then becomes when those functions are not continuous. And we can still find the limit, but we have to wiggle around a bit. Which brings us to our next topic, called the squeeze theorem, otherwise known as how to divide by zero. So let's have an example. This is easiest to see with examples. So we have a rational function here. If the denominator is 0, then we have a very large problem and we can't find the limit because it is non-existent. It's undefined. But as long as we stay away from that, then we could with simple substitution as we did in the previous examples. However, this particular limit asks us with x approaches 5 when our denominator says 5 minus x. So if we use simple substitution here, we're going to get 0 over 0, and we're going to have a very large problem. We can't do that. So what the squeeze theorem says is, given two polynomials that are continuous, we can finagle out a limit between those two, and it will work as an estimation. It won't be perfect because it won't exist in the perfect part, but it will give us a really good guess. Okay? So, how does this work in relations? Well, what we're going to do is we are going to simplify the function. So kind of ignoring the limit for a moment and just focusing on the function itself, the rational function. And we want to simplify this. So my brain immediately says, ooh, my numerator there is my special case of factoring. So special case of factoring says a squared minus b squared will factor into a plus b, a minus b. I can do that. So x squared minus 25 will give me x plus 5, x minus 5. And my denominator here, I don't like that. It's yucky because the number is first and the variable is second. But I can switch this around using this lovely technique of factoring by -1 and then flipping it, and it is mathematically the same. So I can do that. So negative, and then x minus 5 will be the same thing as 5 minus x, mathematically speaking. And then we say, well, anything over itself is 1. So x minus 5 will cancel x minus 5, which will leave us with x plus 5 on top and -1, which is negative x plus 5. Okay, so this is the simplified version of our function. Now that it's simplified, we can apply the limit. So the limit, as x approaches 5, of negative x plus 5 will give us, using our simple substitution, negative 5 plus 5 of -10. This is what the squeeze theorem does. It takes something that we cannot work with and it wiggles it around just a little bit to make it so that we can work with it. Let's take a look at this one. So the first thing that I notice is that they're asking me to find as x approaches 361, and my denominator is x minus 361, so I'm going to get a 0 in my denominator. Therefore, I need my squeeze theorem. I need to simplify my function first before I can apply my limit. Now, this doesn't look nice. Actually, it looks terrible. So, why does it look terrible? That radical. I can't do much with it on the face of it unless I remember about conjugates. I can multiply by anything I want as long as I'm multiplying by 1. And if I multiply by conjugate, its conjugate in particular, I can get rid of that yucky stuff. So let's multiply by the conjugate. So that will give me, by definitions of conjugates, that'll get me the square root of x squared minus 19 squared over that yucky stuff. Okay, so square root of x squared is x. 19 squared is, I don't know that off the top of my head, 361. And then we have x minus 361, not 91, 361, my bad. And 361, and square root of x plus 19. Those will cancel using our anything over itself rule. So we get 1 over square root of x plus 19 as our simplified form. Therefore, it's simplified. We should be able to apply the limit. Should. Not always, but should. So, limit as x approaches 361 of 1 over square root of x plus 19. We now have avoided the 0 in the denominator, so we can use basic substitution. So 1 over square root 361 plus 19, which is 19. So 1 over 19 plus 19. So that would be 1 over 38. So this is what the squeeze theorem does. It takes something very annoying and very complicated, and something that we cannot find the limit of, usually because we have a 0 in our denominator, and we avoid it completely by simplifying the function entirely, giving us a new function that does not have that problem of the 0 in the denominator, and we can apply simple substitution again. Because as long as it's continuous wherever they're asking us to figure it out, we can use substitution to find it. Okay, let's have one more. So we have, as the limit as x approaches 1 of a rational function with a radical in our denominator. So as x approaches 1, our numerator just turned into 0, which is not too bad. We can divide 0 by a number, and we'll just get 0. So our denominator here, 3 times 1 is 3. 3 plus 13 is 16. Square root of 16 is 4. 4 minus 4 is 0. So we get 0 over 0, and we have a problem. So we will simplify this function. We have a radical in our denominator, so we will multiply by its conjugate. So the conjugate in this case would be square root of 3x plus 13 plus 4, which is very annoying, but they told us to, so we gotta. So what will this result in? Keep our factors straight. Minus 1, 3x plus 13 plus 4, and that will give us 3x plus 13 squared minus 4 squared. The square will cancel out the square root. Keep the factors in the top part just to make your life easier. Usually it makes our life easier. Hopefully this time will be the same. And let's see here. So we got x minus 1 square root. So that will give me 3x plus 13 minus 16 3, our denominator there, and I can take out a GCF of 3, can't I? So, that will give me x minus 1, 15 plus 4, 3, x minus 1. There we go. That will cancel out those two. So I am trying to find the limit as x approaches some number that I forgot about by now of square root of 3x plus 13 plus 4 over 3. So what number am I working with? 1. As x approaches 1. Alright, and since we have a constant in our denominator, there is no number that they could possibly ask us to find the limit with that won't work, so we can do this. Substitution. So 16. So square root of 16 is 4. 4 plus 4 is 8. So our final answer will be 8/3.